let's start with the lie at the heart of this talk. So it's not really OCaml all the way down. It's kind of some of half the way down, a bit of the way down. More specifically, what we can do is design hardware, FPGAs, ASICs, in OCaml using a DSL called HardCaml. And recently, I've been looking at how we can do embedded software using OCaml. It turns out quite well. What we don't have, at least for this demo, is a soft CPU in OCaml, like designed with HardCaml. So we're using some vendor IP for that instead. I'm sorry, I will do better next time. And then there's the backend toolchain. So that's like the Xilinx FPGA place and route tools, and quite frankly, life's too short. So let's start with the demo. I did a little state machine for how this can go. So it goes all right on the right. But you will note there are more failure cases. Plugging it in would be good. Should have done that. That's one I didn't note. All right, so I don't actually have to do this. Oh no. Right, that should be okay. Oh, there we go. I think you should just be able to see some blinking going on there. Way! It worked! Now, I know what you're thinking. That's like 10 lines of Verilog, right? Nah, man. That's not the way I roll. That's more like 200,000 lines of OCaml. So I'm going to explain how I managed to do that. So what happened, when I pressed that button, I basically reset the FPGA, which caused it to load the FPGA image, and that has in it, so this vendor CPU, the Microblaze, that's attached to 256 meg of DDR3 memory. There's a little timer core in there which generates interrupts up to the CPU. And then down on the right is the HardCaml design. So that's attached to the CPU via this AviMux thing. That's kind of got the register interface in it as well. And then that attaches to these 3 IP cores. There's a Digi-LED driver, that's for this strip across the front here, written by Mark, wherever he is. Good old Mark. There's a SPI core. SPIs are like standard communications interface between like low bandwidth hardware. And that's attached to a light sensor, which is connected to the board here. And finally, I stuck a little Cordic core. Now, Cordic is like a clever math algorithm for hardware that calculates things like sine and cosine and hyperbolic functions and so on. But it just does it with adds and shifts. Now, where all that OCaml came from is the software that we'll be running. So once the FPGA loaded, it started with this custom bootloader, which then loads a program from SPI Flash and copies it into DDR memory. And that is an OCaml top level, and I'll talk more about what that is later. I should say, those LEDs you saw flashing were actually driven by the bootloader. So as it loads every something like 64K, it increments a counter and then outputs it on the LEDs. Okay, so a quick intro to FPGAs. So they're basically a grid of these things. So the black boxes are LUTs and a register. This is an abstraction. It's not really like this, but it's kind of like this. And they're connected in a grid pattern, and they have local routing between each other. So this local routing is very fast because it's dedicated routing. The blue boxes are switch boxes, and they take the outputs of LUTs and then route them up into what's called global routing, which are resources that allow you to move signals all the way across the chip. So at this sort of scale, I would say this grid goes about 3 miles that way and 3 miles that way. So they're big things. So within each of these LUTs, we have basically formed of this red thing here, which are 16 static RAM cells. And the values in those cells are set up at FPGA load time, and they can be basically anything. The LUT inputs then drive the select of this multiplexer, and basically the 4 LUT inputs can address any one of these 16 cells. And with that architecture, you can basically implement any 4-input Boolean function you like. I should mention that modern FPGAs tend to use 6-input LUTs these days, but that was a lot easier to draw. Coming out of that, you have an optional register. So every LUT has a register. The value that's computed can be registered. Registers are kind of free in FPGA fabric for that reason. But you can also bypass the register, and that allows you to build bigger combinational functions. Just to sort of demonstrate how you sort of set functions up here, if you wanted to build a 4-input AND gate, what you would do is set everything to 0 except the last entry, which you'd set to 1, and that means that when these address 15, so they're all high, it would output this cell, which is a 1, and that would be an AND. Similarly, an OR has a 0 here and all 1s here. So what else is on these FPGAs? Well, I think the most important resource is probably block RAM. So they're RAMs of around 10 kilobits up to, the latest ones have 288 kilobit RAM blocks in them. You have in the order of hundreds up to tens of thousands of these RAMs in modern FPGAs. And what's interesting about that is if you try and add up the bandwidth to all these RAMs together, it's ridiculous. It's absolutely enormous. And using that appropriately is why FPGAs can be pretty fast. Another resource are Dsp blocks. So they're basically multipliers made out of actual silicon rather than the fabric. These days they're a lot more complicated than that. They've got pre and post adders and subtractors and so on for various specific applications. And they're also set up to implement floating point adders and multipliers efficiently. Then you've got your clocking resources. So these are PLLs and, well, they used to be called DCMs. I think they're MCM somethings these days. Basically, they can take a clock signal in and then produce 6 different clock signals out, which are some multiplication and division factor of that input clock, and also phase shift it. And also they do some magic, I'm not sure quite how this works, where they can align the clock across the entirety of the silicon because there are propagation delays there and they matter. So when you clock logic, you have to do it in a specific way in an FPGA using these clocking resources. There's a whole big manual about configuration of them. So this design, for example, is loading out of a little flash. It commonly will do that. Another thing that's worth noting is most FPGA boards these days come with a USB interface, which allows you to program the FPGA from your PC. That's really useful. Then there are the pins on the FPGA. These are complicated beasts with an extremely large manual. I was talking to a Xilinx guy once. He was saying that in top-end FPGAs with these huge serializers, 50 gigabit serializers, half the die is now set aside for just the pins. It's crazy. And then over the last 10 years, the FPGA vendors have started putting lots of what they call hard blocks, so it's actual hard silicon for specific functions like PCIe and gigabit Ethernet, and more interestingly perhaps, there are a bunch of FPGAs which have ARM cores on them, and pretty high-end stuff, sort of similar to your mobile phones, like quad ARM, running at 1.2 gig or something. Okay, so quick intro to RTL. There was a cool lecture I saw a while ago, I thought I'd point this out, which shows how the abstractions build on each other. And I think it's pretty useful to sort of understand where this stuff fits in the general scheme of things. So we're living down towards the bottom, and really it's the combinational logic and the clock logic is what FPGA design is mainly about. So combinational logic is things like adders and one-hot decoders and one-hot encoders, a bunch of sort of standard RTL design blocks, and you stick them together with clock logic, which are basically registers, but also these RAMs. But these days, with the advent especially of soft CPUs, you'll tend to get into sort of more embedded programming as well to get these things running. So you start thinking about stuff like instruction sets and operating systems. Instruction sets in interesting ways. Like you might think that's just for a CPU, but you'll also build like programmable state machines which have a kind of instruction set, so it kind of overlaps there as well. In the operating system world, you may not be running Windows or Linux on this, or you can, but there are RTOSes that you'll play with, and you almost certainly have to get familiar with things like the C library that's provided for the compilers. And then for us, we do OCaml on this as well. Why not? So the industry standard for developing RTL is VHDL and Verilog mainly, actually probably System Verilog these days. C is also getting a big push, so there's a few variants there. There's System C, which is more a modeling language and is made to look like VHDL and Verilog, although there are some crazy companies who've tried synthesizing that too. And there are also a bunch of tools which can take untimed C descriptions and turn them into hardware with fairly varying results, I would say. One thing that I always found interesting is, these languages have taken over hardware design, they really have, but they were actually conceived as documentation languages. They were never meant to do anything except document designs. That's why they're awful. So what are they? They're event-driven languages, so they're like nothing you've ever come across before. They're totally weird. The idea is you've got these always blocks. On the right-hand side, you have things like assignments and if statements and so on. So they feel like little imperative language, a little imperative language. But this stuff is always triggered on what's called a sensitivity list. So this first one will update X. So if you can't see that, it says X equals A or B. It'll only update X when there is a change on the signal A or the signal B. And that's how you describe combinational logic. The next one down describes a register. So here, the sensitivity list is change on the positive edge of the clock, which means on the transition of the clock from low to high. And that will cause X to be loaded into Y, and it will hold its value for one clock cycle. So that's how you describe registers. Now, an RTL design is a passive thing. So it reacts to signals coming into it. And so in order to actually do anything with this within Verilog, you need another language, which is for generating events, generating transitions. So you've got things like this. In particular, it's this #5. So this says set A to 1, then wait for 5 time steps, then set B to 2, wait for 15 time steps, and do something else. This is how you get events into the system and get it processing stuff. So when you do this, this will trigger, and you might have a clock generator causing that to trigger. But none of this can be synthesized. This is like the other half of Verilog. Half of it can be turned into hardware, half of it can only be used for test benches. So the commercial simulators generally in use, mainly, I think, Model Sim and VCS these days. Riviera Pro still around. In the open source world, we've got Icarus Verilog, which is a pretty decent Verilog simulator. GHDL, which is a VHDL simulator that's improved massively over the last few years. And then Verilator, which is a kind of interesting tool that takes Verilog and converts it to a C++ blob, which has been pretty heavily optimized, but with a number of assumptions. Like, you can only put synthesizable RTL into it. And under those assumptions, it can create a very fast model. And that tends to actually get used a lot commercially as well. One thing that is lacking in the open source world, and this is becoming more of a problem, is any sort of system Verilog support. So all the FPGA vendors have converted their IP to system Verilog, but there really isn't anything out there in the open source world to simulate it. So this is what it looks like when you're an RTL designer. I spent far too long watching those things. First of all, look at all those buttons. There's a lot of buttons. But this thing here, this window, that's like how you debug RTL. That's showing all the transitions going through time and all your signals. Now, this was a tiny little simulation I did. I mean, these things get absolutely gigantic. And yet, that's how they designed your iPhone. I mean, it's amazing stuff. There are a bunch of sort of slightly newer technologies that came around roundabout with system Verilog. So there's things like constrained random stimulus generation. So the idea there is you're going to generate random data into your simulation, but you want to constrain it so that it ticks interesting paths in the simulation. So for example, say you've got like a network packet processing core, and it only works with some specific protocol. So you can tell the tool that the packet should look a bit like this, and it will generate a bunch of random stuff. And alongside this, the coverage-driven frameworks that the tools provide, that allows you to like dig into interesting parts of the design kind of automatically. I think more interesting are the temporal assertion-based property checkers. So these things allow you to say, like, an event occurs, I need some other event to occur within 5 clock cycles, say, and various temporal events like that can be described. And then when you run the simulation, the simulator will check that these properties are always true. The really interesting stuff is formal verification. And that takes the same sort of temporal assertions, but will prove that the properties hold true for any trace using extremely black magic. But it's very cool stuff. OK, so getting to HardCaml. At its heart, it's something like this. So you've got variant type with registers and memories and multiplexers, and op hides some details. You've got adders and XOR and so on in there. So at this point, I think that looks a lot like a standard OCaml AST for a compiler. Then we come to wires, where things get a little different. And so wires can be created, then used, before they're actually assigned. And what this allows you to do is create cycles. And I think at this point it's better to think of this thing as a graph of hardware nodes with connections, which may be cyclic. In terms of the API, I mean, there are an awful lot more functions than that, but this is really the core. Everything kind of gets built on this basic course. You've got sort of general arithmetic, logical operations, comparisons, constants, muxes. So bits are kind of interesting. Like, what we're dealing with are not fixed size integers or anything like that. We're dealing with fixed size, but variable sized vectors. Vectors of any size, be it 1 bit or 1,000 bits. And these functions work over all these different sizes with some rules. So down towards the bottom, we have like width. Well, width's an interesting one, actually. It's worth noting that any signal you've got access to in a HardCaml design, you can query for its width. And that allows you to create self-adaptive designs that just look at a width and just construct the appropriate logic for that. Because it's very easy to do that with this, whereas in Verilog, it's a real nightmare. The other one is instantiation, or inst. That allows you to kind of put a hole in the HardCaml design that you can fill in with VHDL or Verilog later, and that allows you to work with third-party IP or with vendor primitives and macros and so on. Okay, so the general rules there, if the operation is unsigned or doesn't care about the sign, it ends in a colon. In a few cases, the operator ended a plus. That's where you have to care whether it's signed or unsigned. So multipliers are an example of that. So an unsigned multiplier has a different architecture to a signed multiplier. Similarly with comparisons. That tends to mean there are quite a few checks that occur at runtime. Although in hardware parlance, it's not like simulation time or anything like that. It's at elaboration time. It's when the graph that describes the hardware is fully constructed. So we're quite strict about things like signal widths in the API. So here we're adding a 2-bit constant to a 3-bit constant, and it says no, can't do that. There's a kind of technical detail in the library which is not well loved here, but it still exists. So we have this idea of the API over 2 different types. Bits compute values. So here we see const add 2 to 1, and we get 3 out. With signals, you're recording the computation. The place where this is still used is we design hardware using signals, so it describes the computation or the graph that you want. And then when we go to simulation, we use bits to drive values into the ports. Sequential logic in HardCaml, there are actually only 2 primitives, so you can create registers, or you can create a memory primitive, so it's technically an asynchronous read memory. And we use that to build up proper memory structures that can be instantiated in FPGAs and ASICs and so on. And we also build stuff to build state machines. For example, the always DSL. So this models the Verilog always blocks I showed you before. It's a little bit different. But it basically provides a way of assigning to registers or even combinational values under guarded conditions. So you've got ifs and switches and so on. And you can decide when to assign values to registers. And we tend to use this mainly for state machines, which are like a switch statement with the case listed, and on the condition, you can set the next state of the state machine. So, as we're saying, HardCaml just provides a simple memory primitive, and then it builds proper memories by applying a register to the address port or the output port of the memory. That will create a read before write or a write before read memory. That should then be inferred by the vendor synthesis tools. They say it does. It doesn't always. As is actually the case with Verilog as well, there are more complicated primitives, like just a standard true dual port RAM can't actually be described properly in Verilog and automatically synthesized, so you have to use macros. Same with HardCaml, you have to use macros for that. Okay, so a quick example. This is kind of what I consider the hello world of hardware design. A little fur filter. So across the top, we've got 4 registers. The input enters at the left, and then on each clock cycle, it steps down the pipeline. So effectively, you have a window of the last 4 samples. These are then multiplied by a constant coefficient and added in a tree of adders. So in HardCaml, that would look something like this. So this is constructing those registers across the top, returning the window of registers as a list. And then we just instantiate the registers, map across the coefficients and the registers, performing a sign multiplication. And then we've got this tree function, which will take a list in and create a balanced tree down to 1 value. And that could be any binary operator. So for testing, HardCaml has built-in cycle-accurate simulation. So that's the same as Verilator, which I mentioned before. It doesn't support event-driven simulation, at least not at the moment. So it looks something like this. You build the simulator, and then the thing at the bottom is where the real stuff happens. You set input ports to the circuit. You call cycle, which steps the simulation on one cycle. It evaluates one clock cycle, and then you can read the outputs of your circuit. And you do that again and again and again, stepping through the states you want to test. There is a problem with that, though, and that's fine for simple hardware, but most hardware isn't that simple and will have multiple independent input and output blocks of signals. So you might have, for example, 3 FIFOs going in, a register interface, a memory interface, a bunch of other stuff. And in that model where there's just one flow control, it's like you effectively have to turn your whole test bench into a state machine to interact with all these different things. So we've written this thing called HardCaml step test bench, which you can pretty much think of as async for hardware test benches. So it allows you to have multiple independent flow controls, which can deal with different interfaces and ports on the hardware design, but still interact with each other. A very cool feature is we have this Microblaze Simulator, written again by good old Mark. And we integrated that with HardCaml step test bench. So that means we could load a Microblaze ELF file, so that's a Microblaze program, simulate it with this instruction set simulator, which is not hardware. It's not trying to simulate hardware. It's simulating the instruction set, so it's fast. So I don't know, maybe a few megahertz fast. But that can actually interact with a hardware design attached over the standard bus interfaces. In this case, it's like AXI bus for the Microblaze. That's really very, very powerful. So this thing looks, well, it doesn't really matter. I think the things to note are multiple tasks, they get spawned, you can wait for results, you can return results, and it's all in a monad. Of course it is. It's always in a monad. So for debugging, I don't like GUIs, so I wrote a text-based waveform viewer. So the support we have in HardCaml, there's an interactive terminal-based waveform viewer with scroll bars and the whole shebang that I actually do use a lot for debugging stuff. But if you want to, it can output VCD files, which are standard Verilog waveform files, and they work with any waveform viewer in particular. GTK-WAV, which is an open source waveform viewer, it's actually pretty good. There's also a bit tighter integration with HardCaml simulation in that it can start a simulation, fire up GTK-WAV, and pump data across to GTK-WAV for it to be viewed while the simulation is actually happening. And a new feature is we now have waveform expect tests, which are super cool. You may have heard we quite like expect tests around here, and they look like that. So what does this mean? Well, this means that our continuous integration system is now checking HardCaml simulations through the data dumped in the actual waveform. So when something goes wrong, you get a diff, and you can go and fix it. Now, there are cons to this. It's like this stuff is good for maybe 30 clock cycles before it just gets too far off the other side. That being said, it's still incredibly useful for looking at little protocol details and having them actually written down in code. There, this is how it should work. It should not change. If it does, you need to fix something. Okay, so I thought we'd have a quick detour into the world of formal verification. So let's say you have a 10-bit adder and you want to prove it's right. Now, you think 10-bit adder, Why would you do that? Well, it turns out a lot of papers get written about adders, a lot of papers. So you've got 10-bit adder, 20 bits in total, what's that? 1 million test cases, no problem. Well, if you want to test 200 bits, well, it just ain't going to happen that way. So enter SAT solvers. They're cool things. So the idea behind this is you've got a Boolean function, so it produces true or false of some number of input variables. You can go in and ask the SAT solver to find an assignment to the input variables that makes the Boolean function equal 1. If it can do that, it returns SAT, and it tells you what the values of the input variables were. It's not if it can't find one, it's if there is no assignment, it will return unsat. So there's a trick we need to play here, because what we usually want is to prove that a property is true, always. So the trick is we actually ask it about the negation of the function. And so what happens is if the SAT solver returns unsat, it's saying it can never make not f1, which implies that f is always 1. Always 1. So that's it proven. If you get sat, the cool thing about it is it will tell you where it went wrong. It will actually tell you, here's your bug, and this is what caused it. So in HardCaml, we've got reasonable verification support now. We can convert any combinational circuit into, well, when I say any combinational circuit with 1-bit output, so a property over a combinational circuit, can be converted into a SAT problem. We've got a little framework for sequential equivalence checking. So the way we used that is we were porting some Verilog to HardCaml. And so I had this HardCaml design. I was like, how do I show it's still the same? Well, I used this open source tool called Yosis, which converted the Verilog into this low-level netlist, which I could then load into HardCaml and then form a SAT problem comparing the outputs, say, are all the outputs always equal to each other? The trick here is that both circuits have to have registers in exactly the same places. To lift that restriction, we have bounded model checking. So I've got a bounded model checker. I don't necessarily trust it yet, but it kind of works on small cases. It's also got LTL property specifications. So with these things, you could compare two circuits. They could have different states, and you can ask it over a trace of 100 cycles, are these things the same? And it can prove that. It can't prove anything about the 101st cycle. That's why it's called bounded model checking. But nonetheless, it's a very, very powerful technique. Okay, so this software stack. So as I mentioned, it's running on the Microblaze. So that's a Xilinx soft CPU built out of the fabric of the FPGA. It's a standard RISC thing. But the most important thing is it's got a GCC-based cross-compiler. What are we running? Well, it's the OCaml bytecode. So in the OCaml world, there are two ways to compile code. You can either compile it to native code if the compiler supports your architecture, which it doesn't, or you can compile it to bytecode, which is like generic and runs on a C-based interpreter called the Zinc abstract machine. So the first step was for me to cross-compile the OCaml C runtime with this interpreter in it. Then we need to get all the libraries. So as it turns out, you can just build the bytecode CMA libraries for OCaml, just like normal on x86. In fact, they're being built by a 64-bit compiler, even though they're being run on 32-bit. You then construct a top-level executable, bytecode executable, and pass this magic flag called output obj. And what that makes OCaml do is write a C file, which has an int array with all the bytecode for your program embedded in it. And then you can compile that with your cross-compiler. The tricky bit is you need to link all the C stubs that were referred to in those OCaml libraries into your final application to run on the processor. So you just need to compile them, but you've got to go and find them within the source code tree. It's not that easy. But anyway, there actually aren't that many of them. I think I found maybe 40 C files in total. So what isn't working? Well, signals don't work. That's actually quite annoying, and I think I could probably make that work. There are no threads, and there are no threads. So you could get around that if we ran this thing on top of an RTOS, but I bet the threads that an RTOS provides are not quite what OCaml expects. I'm not sure. I'm not sure it's worth it. Unix. I mean, yeah. There's no file system. Well, how do you expect Unix? But what does work, well, base, core kernel, async kernel, they're all up and running in this thing. And rather neatly, the OCaml top level runs in that. So that is the OCaml compiler also running on the FPGA. Okay, why wouldn't you want to do this? Well, the smallest executable you can get out of this is about 400K, which in this world is enormous. When you start layering on the Jane Street libraries, as it's not quite true, 1 meg, it's actually nearer about 700K. When stuff starts linking in, you're using more features, it quickly gets up to the 4 or 5 meg range. And then when you put the top level in with all this stuff, well, add it up at 23 megabytes. Ouch. I mean, it's understandable in a way. When you're doing the top level, like it can't optimize out stuff you're not using because you can potentially use anything. So that accounts for about 7 meg of it. But it turns out these CMI files, which are used by OCaml for type checking the code you write, are enormous. So they took up about 16 odd meg. Just details. Okay, so let's see if we can get some demos working then. It's not that one. Okay, so what do I need to do? I need to 33857. Right, let's see if this is working. Yeah. So, what just happened there? Well, the processor is redirecting its standard in and standard out through this USB cable up to a driver on my laptop, which is then bridging that across onto a TCP socket, which I'm then attaching to with netcat. And anyway, I stood in, stood out there, goes down to there. When I typed that, so I typed let a equals 1, that was compiled by the FPGA, or at least by OCaml on the FPGA, and it showed the result. So, if I can get. Okay, so hopefully you can see that. So this is a pulse width modulation demo. So the basic idea, let me run that again. All right. The basic idea is these LEDs could only ever be on or off. So pulse width modulation is a fancy way of saying we turn it on for a little bit and then turn it off, but do it really, really fast. so it looks like it's like half intensity instead. And we do that over and over again with intensity going up and down so the LEDs breathe, as Brian likes to call it. So in terms of code, it's just a bunch of for loops setting the LEDs to these values, either on or off. Oh. Is it working? Yay! I was so excited when I got the strip that this is all I wanted to do with it. That's basically all I've been doing for weeks. It's great. So that's the little Cylon demo. All that's happening there is we basically set the next LED to the left until we get to the end, and the next LED to the right. There's a little busy loop after setting each LED, so it just doesn't go so fast you can't see it. And every time, just before we set the LED, we run through the entire strip and halve the current intensity of all the LEDs. And so that gives you the tail running behind it. Okay. Ooh, there it is. Light sensors. I think it's 2000. Right. Yeah? Is it still going?
Yeah. Oh, yeah.
Have I done it too long?
Make it really dark.
Oh, I think it's just stopped.
Too late. No, it won't.
Can we run it again? Okay, so that's a little what's called a PMod that's been attached to this board. If you go to the Digilant website, there's like 50 or 60 different PMods you can buy and attach to this and have a play with. This particular one is obviously a light sensor. So that's read via the SPI protocol I was talking about before. So what happens here is, this is like doing the SPI transfer. So you start the SPI hardware, wait for it to be done, and then you read out the data. The way the data is formatted, it's basically bottom 4 bits are nonsense, and then 8 bits are the current intensity value. Now, I'm not entirely sure if it's like picking up the flickering of the lights, or it's just like not always very accurate. So you have to average it for quite a while to get a nice, sensible value. So this reads it, I think it's doing it about 500 times, taking an average. And then, as you could see, it would show the intensity of light in green on the LED strip. So that's what's done here. So you've got this, you basically take the 8-bit value and shift it down to 32, because this has got 30 LEDs on it. Okay, this takes a wee while to compile.
So is the LED underbar strip written in HardCaml also, or is that written in Verilog?
The LED driver.
Yeah.
So the Digi-LED driver is in HardCaml. It was written by Mark a few weeks back. So it's a funny wee thing, actually. It's like got one one bit that is used to drive the RGB values for all the LEDs across this. And so you have to like send a pulse width modulated bit pattern to tell you when ones and zeros, and you program the first one, put it into some sort of reset state where it holds its value, and then you're programming the next one, and so on. You just strobe across the strip doing that. Running? Yeah, great. So this one's a bit more complicated and, not as much fun, I'd say. But anyway, so here we're using the Cordic core that I mentioned that's in HardCaml as well. So the Cordic core is actually pretty general. It'll do all sorts of functions from like ATAN2 to hyperbolic functions to coordinate rotations. Here I'm using it the simplest way, which is just to calculate cosine. So this is how you configure it. There's 4 inputs. You set the x, y, and c inputs to these fixed values. And then each time you want to compute cosine for an angle, you set z, start it, and then just wait for the core to be finished. It actually computes cos and sine at the same time. We're only interested in the cos one. It then takes that value. There's this horrible bit of logic. So the algorithm will only converge in it's like minus pi over 2 through to pi over 2. So what I have to do here is take the argument, basically I reduce it down to 2 pi, and then for each quadrant you can use symmetry to work out how to project it into the quadrant that converges. And then what we're doing is just displaying the cosine function on the LEDs. So you use the intensity of the LED to say the value, except if it's negative, I think, was it green, and positive, it's red. And then you run through various iterations where you just increment the phase by a little bit, and that makes it walk across the LED. Right. Now we've got my favorite one. Okay, so this takes a little while to load. So this is async running on an FPGA, which is just crazy stuff. So what we're going to do is something similar to the Cylon demo that I did at the start with the LED bouncing across the strip, except what we're going to do is fire up 3 separate strobes that run from a min to a max LED and just bounce in a range with a specific color at a specific speed. So we're going to fire up 3 threads. So one is going to go on the left half of the LED strip, one's going to go on the right half, and then another one's going to go across the full strip. And then we run a 4th task, which is doing this halving of the intensity to display the trail. So what we need to do. So happy. And yeah, so to do this demo, it took about 200,000 lines of a camel. Okay, so getting this stuff released, as ever, it's all last minute, but we are, I think, maybe a day, maybe 2 from getting HardCaml, the latest version of HardCaml released under the Jane Street repos. It's a pretty major upgrade over the last open source release, especially in terms of testing. It's got so much more testing now. It's in much better shape. Planning on a couple of further releases, some to tidy up and release some of the older libraries that I've got, so like the Waveform stuff. And then there's some new stuff like the HardCaml step test bench, the Microblaze Simulator, which I think we'll get out as well. I say 3 months. We'll see. But hopefully. Now this demo code I'd like to release as well, but oh man, it's a hack. It's awful. But I've started tidying it up. The really tricky stuff, if we want to put this out on OCaml, is figuring out how to compile or cross-compile the C code. So I'm thinking of setting up like OCaml remote, or like a remote repository with packages which just take the standard like Jane Street async, download it, compile it, and then do a patch which will compile the Microblaze library as well and stick it somewhere that it can be used. So I think it's actually doable. I will try and get something out in the next week or two on that front, so you can have a play with this stuff. And that's it. So, thank you very much. Yeah.
So the OCaml Temporal that you had running on there, that was running on an IP core that's flashed on the FPGA, is that right? Or is that not right?
No, that's right. So it's running on a soft CPU. It's this thing called the Microblaze, which is basically a 5-stage RISC CPU that we've included in our design to run C code.
I guess my question is, why would you want to do that rather than run on the processor, which is probably a lot faster, cheaper, less power?
Well, there isn't one.
There isn't one.
Yeah. So there's no processor on this board, or the FPGA we're using here doesn't have a processor. There are FPGAs that do have processors, but we don't have one.
Why would you use one of those if you wanted to run on OCaml top level?
You could, I would say. If you had an FPGA which had one, you would use one of them for sure. If you don't, then you're down this rabbit hole.
Surprisingly, the really high-end ones we often use in the industry and finance don't have the system-on-chip design.
And it wouldn't be better to, if you really wanted to run bytecode or just instruction, you would want to have a network interface that talks to the custom CPU.
Well, if you want to know what's going on in the circuit itself, it's kind of hard to do anything else.
So you're going through a bit of trouble in order to execute the OCaml bytecode on top of the Microblaze. Have you considered, it might be a bunch of work, but executing the bytecode directly in a soft design?
Yeah. Oh yeah. I started looking at that actually. It was a while ago now, but I did write a little state machine that could execute about 3/4 of the OCaml bytecode VM directly in hardware. And I would love to get back and finish that. So it's on GitHub, HardCaml Zinc. There's a project for that. The place I got a little bit stuck is like, yes, you can do that, but actually there's still an awful lot of OCaml that's implemented in C, so you need a RISC CPU anyway. So I started doing that. It's like, oh, I need a RISC CPU, so I started writing that, and then I got a job. So. Yeah.
There was one slide where you said there's no Unix here. Can you just elaborate a bit more on what you mean by that?
So the Unix module in OCaml deals with things like file systems and networking. On the soft CPU here it's not connected to a file system at all. So none of that stuff, like you can't fopen anything because there's nothing there. At the moment, we don't have any network. Well, that's not true actually. In reality, that design does have a network interface to this little RJ45 connector. I just haven't got it working yet. So potentially, we could consider doing networking stuff, but we then have to mint up like a sockets emulation layer for it to work with Unix. And chances are we'll just use low-level APIs instead.
So I'm slightly confused. So is the HardCaml DSL being like compiled down or synthesized down into like lookup tables and like routes, or is it just running?
No.
It's just always running as bytecode.
No, so the HardCaml DSL is used to describe a hardware design as an in-memory data structure on your PC, right? That is then processed and turned into Verilog, and that's where it's handed off to the backend tools. So I did say I'd speak about pros and cons of this stuff. So that is one of the big cons of using HardCaml. The Verilog that's generated is entirely unreadable. Right? Nobody wants to go near that. No, that's my job. That's what I have to do. So, you know, and because the backend tools are designed for like Verilog and VHDL, like there's a tension between like getting the right names from a camel all the way through to the net list, so you can do like time enclosure and see the right names on your nets and so on. It is doable, but you have to be careful. Yeah.
Any comparisons between some of the stuff you've done here in BlueSpec? Because that's like the Haskell.
Yeah, sure. So maybe like $100,000. And no, it's yeah, it's completely different. So this HardCaml in terms of abstraction is pretty much the same as Verilog and VHDL. It treats designs the same way. It doesn't really try and infer like where stuff should happen on what clock edge or anything like that, which BlueSpec does do. I like BlueSpec. I like the idea of it. I've never actually used it. I've just read papers about it, but I like the idea. And so we're definitely thinking about looking into like a DSL on top of HardCaml, which models like the atomic actions of BlueSpec, and seeing where that takes us.
Some of the stuff you do, when I was using BlueSpec, it generates a very large code, and it actually sometimes I run into timing problems. As you said, the timing code.
Yeah.
How does HardCaml make that easier? Does that make it easier, or what do you do if you run?
Yeah, so I mean, if there's a timing problem, there's something wrong with your architecture. Okay, so BlueSpec, I think, like because it's a compiler which will change your design, will change your intent. Not really your intent, but you know what I mean. It creates a microarchitecture for you. It's kind of pushing you down a route where I guess it's quite difficult to get out of that. HardCaml, it's not like that. The thing you write in HardCaml is exactly the Verilog you will generate, and therefore the architecture you will pass to the tool. So if it's failing timing, it's your fault. That being said, because it has to go through this translation to Verilog, the thing you must do is basically apply in your HardCaml design a name to every single register. And that means when you get timing reports, you actually get a timing report from a name to a name. As long as you do that, it's okay. It's workable.
So why is the Verilog that's generated so unreadable? It seems like it maps pretty closely to Verilog then, in like the DSL.
I don't know if I have a good answer for exactly why it happens. I mean, I think most of the generation systems I've seen that are similar to HardCaml have the same problem. Yeah, I'm not entirely sure, to be honest. It just is awful. You don't want to go near it.
Have you thought about using this, right?
Absolutely. That is the processor I want to replace the Microblaze with. And I will eventually convince Ron that I can do this. And it's a good idea. No, there's a serious reason for this, actually. It's like, we're trying to get these tools into like our workflow, and like getting these huge vendor tool chains as part of this is a real problem, especially when they're upgrading all the time. And like, it seems to me that having control over that bit of actually pretty core technology to us would mean that we get to decide when we upgrade this stuff, and we get to decide when we upgrade the compiler. And I think it would just be a lot easier for us to manage. So I think there's really good technical reasons for doing it, and I kind of want to do it as well.
I'd love to hear about about exactly why the bytecode is running on the chip on the card. Is it like just for demo, or in a production environment you do the same?
Oh, it's just because I can.
Okay.
Like, I say there's no practical reason. There is practical reason, actually. We are thinking about using these soft CPU. Well, we are using these soft CPUs in our designs. At the moment, we're having to write C code, and that's kind of anathema. And actually for good reason. So, like, you know, some of this code will be fairly critical. It might be like kill switches for designs that go and do like real stuff. And it's got to be reviewed. And the way we know how to review code is OCaml. If there's a whole pile of C code getting injected in there, it's just not good.
The bytecode, but not the interpreter itself.
No, we wouldn't have top level is just a bit of fun, just because I could.
That's what I thought.
Yeah, and I think I don't know. I mean,
It would be a great debugging tool if all of our FPGAs you could like log in and use the OCaml top level.
sure. Oh, wouldn't it just?
It would be insane, but
And check your email and play Doom.
yeah,
Yeah.
everything should host you.
And Emacs.
That's too
Yeah, that's not possible. It's just cheap.
Yeah, I can actually see using the top level like more generally just for like early design tasks where you just like want to go in and poke some registers in the design and see how the thing is working. If you got it there, why not use it? Sorry, yeah.
So like the soft CPU, I'm still wondering like why it's there. Is it there for administrative or like debug stuff?
Yeah.
Will it ever be on the hot path?
No.
Never in the hot.
You were mentioning that you were using SMT software for the verification stuff. What are you using?
I'm actually using SAT stuff at the moment. I haven't figured out how to do this weird SMT lib language. Although that being said, recently into our repos Z3 went in and it's done with the OCaml bindings. So that's a much nicer interface into it. So when I have a bit of time, I really fancy going and have a play with that because I think it would just like be a quick change. So instead of using SAT, so like mini SAT is the main one I use, I can switch to Z3.
Yeah, Z3 is beautiful.
Yeah.
I'm going to take one more question. Okay, so for those who are interested, a bunch of us are going downstairs to a pub where there's some free food and drink, and we have a room and all that. So you should feel free to come down and ask more questions about hardware or whatever. So let's thank you.